All right, we're getting near the end of this lecture. I wanted to work through some properties of the definite integral with you. So first off, if you decide for whatever reason to integrate from a to a, and these are the same points, then you're computing the area over a single point, but points have no width. They have width 0, and so this integral will always be 0. The integral from a to a of anything is just 0. We typically think of property 2. I'm always going to think of a being less than b, and so we typically write our integrals, the integral from a to b. The bottom number is where you start on the x-axis and you're moving out to b. But what if you flip it? What if I want to go from b to a? What if we go this way? And well, what you're doing when you compute delta x in that case, it's going to be opposite sign. It's going to be negative. And so you actually get negative the integral from a to b of f of x dx. So if the bounds are out of order and you need to switch, then you just switch the sign. Let me squeeze in a little example just to show you this. So example, if I want to go the integral from 1 to 0 of x squared, this is the same as negative integral 0 to 1 of x squared. And we just did this part. We just computed in the 2 videos ago that the integral from 0 to 1 of x squared is 1/3. So this integral is negative 1/3. So anytime you need to switch these numbers to get them in the right order, you just pop a negative out. Third property, what happens if you integrate a constant? What if you integrate a constant? Well, let's sketch a picture off to the side. I'm stuck working in pink, but that's okay. So here's a, here's b, here's my constant k. And if you want to find the area under k, well, it's just the area of a rectangle. It's just b minus a times the height k. So that's exactly what this property is. This is just b minus a times k. So example, let's just squeeze an example of each one of these in. If I want to integrate from 2 to 5 of pi dx, I just get 5 minus 2 is 3 pi. And so those are really nice. Integrating constants is easy because it's just rectangles. Now, next property, if there's a constant in front of your function, you can actually pull it out of the integral. Why can you do this? Because integrals are limits, and we said way back in chapter 1, you can pull constants out of limits, and they just tag along for the ride. So you can just pop the c out. That's really nice. Let's see an example of this. Maybe I want to integrate 0 to 1 of 10x squared dx. I don't know how to do that, but if I pull the 10 out, I do recognize the integral from 0 to 1 of x squared. We did that one. That's just a third, so it's 10. Well, it's just 10/3. And let me show you a little bit more about what's happening. If I just sketch you a picture here, here's x squared, here's 10x squared. And so when you multiply the function by 10, the area scales as well. So you're multiplying the function by 10, pulls it up, and you actually get more area by a factor of 10. So somehow this shouldn't surprise us one bit. Property 4, you can break integrals up over sums and differences. So if you have f of x plus or minus g of x, then you can integrate a to b f of x plus or minus whatever it is, a to b g of x, which is really nice. So let's see an example of this. So example, if I want to take the integral from 0 to 1 of x squared plus 5, again, I don't know how to do that. Well, I do, but as a class, we don't know how to do that yet. And so I would break this as integral 0 to 1 of x squared dx plus integral 0 to 1 of 5 dx. And I know how to do both of those pieces. The 0 to 1 x squared is a third. 0 to 1 of 5 is just 1 times 5 is 5. So we end up with 16/3. So you can compute integrals over sums by breaking them up. Sums are differences. All right, the next one is kind of interesting. So if I have a function, the same function now, f of x, but my interval goes from, let's say, a to b, and then I have b to c. So if I integrate from a to b of f of x, so this is this integral, plus the integral from b to c of f of x, that's this area plus this area when f is positive. And so it shouldn't surprise you one bit that this is the same thing as the integral from a all the way out to c of f of x dx. And I've squeezed an example in here. We're a little tight on space because because I made it tight on space. So we're asked to find the integral from 0 to pi of sine squared dx, given that the integral from 0 to 3 pi halves is 3 pi fourths, and the integral from pi to 3 pi halves is pi fourths. So let's write down what we're given. So we're given 0 to 3 pi halves. We're told this big interval, and we're told this one is 3 pi fourths. We're also told 3 pi halves to pi is pi fourths. And now we can see, okay, what we're after is this interval. We want to go from 0 to pi. And so you know this one plus this one has to be the big one. The big one is 3 pi fourths. This one is pi fourths, so you just subtract. So our integral, I'm going to have to squeeze it here, our integral 0 to pi of sine squared x dx is just going to be 3 pi fourths minus pi fourths, which is just pi halves. So that's that. All right, so those are the properties of integrals that we're going to need. The first homework problem just asks you to play with these properties. I'm not going to ask you to set up any sums or anything like that. I just need you to have some idea of where this integral comes from. You've got to know that it's a limit, there's rectangles, and it has a lot to do with area, although, like we said at the first comment, it may itself not be area when the function dips below the x-axis, and you think of it as the sum of all the positive areas and then minus all the negative areas. All right, so I'll stop this video here. This is the end of the first Chapter 5 lecture, and the homework problems from 5.2 are posted, so you are ready to roll.